So, conjugate acid-base pairs. This is just a fancy way of saying the two things that went together before. Okay? Don't worry. It looks hard, but it's not really. You've already kind of known what was going on. They differ by one proton. The conjugate is always a product. In case you conjugate something as a product, that tends to kind of mix people up. And we're going to use the examples that you have on your previous sheet, on sheet 1, as a way of labeling our conjugate acid-base pairs. So the first example I think we had is HCl, is that right? Yeah. Plus H2O gives you H3O plus and Cl minus. Is that the first, that's the example from page 1 that you've done when we talked about proton donor, proton acceptor, right? So who here has donated a proton? HCl has donated a proton, right? There's a proton, it's donated it to water. Hands up if you get that. Good. So because it's a proton donor, we call it an acid. So this is an acid. Everybody fine with that so far? We did that yesterday. And water is a base. Okay. What did HCl, what's left over out of the HCl? What's left over? The Cl minus. So this is the conjugate base of that acid. They differ by one proton. Do you see how they differ by one proton? You see the H? No, you don't. They differ by one proton. This is the base. You knew that because it accepted the proton from yesterday. So this is called the conjugate acid because these guys differ by one proton. So these guys are a conjugate acid-base pair, and these guys are a conjugate acid-base pair. Okay? It's really that simple. The things that people make mistakes on is they don't realize that conjugate always has to be on the product end. But this isn't H3O plus isn't always a conjugate acid. It is if it's a product. But if as soon as I'm reacting this with something else, then it becomes a base or an acid or whatever, not a conjugate. So students tend to think, oh, H3O plus is always a conjugate acid. No, sometimes it's an acid, because sometimes it's this side. Okay, so the next one you did in your thing was CH3CH2COOH. Is my memory correct? Is that the second one on your sheet that you've already got?
Yes.
Somebody speak. So you're looking on page 1
Yes.
of that booklet, and you're seeing these examples, and you've already got acid underneath there, right? And you've already got base underneath the water, correct? What is the conjugate base? What did this become?
CH3CH2COO.
Right. CH3CH2COO minus is the conjugate base. Get it? And what's your conjugate acid? H3O plus is your conjugate acid. Okay? And your last example on that sheet was NH3 plus H2O went to NH4 plus and then OH minus. And we said that this was a base and this was an acid. We made the point that, oh my gosh, water has been in a base the whole time and now it's an acid. Oh, water can do both things. Oh, we call that amphiprotic, if it can accept or gain a proton. Okay, so the base there, the acid there, so what's the conjugate acid? What differs by one proton? NH4 plus. Conjugate acid, and an OH minus? Conjugate base. And most often, this is how we apply it. Here's the reaction all written for you. Tell me the conjugate acids and base pairs, which you've just done. Okay? A little bit more tricky to see is this number 2 question. So, organize the following acids and bases in a table that lists the conjugate pair. Why isn't this scrolling down? Hold on. That lists the conjugate base pairs in their relative strength, strongest being in the first table. Okay, so this is what I'm wanting. I'm wanting a table, and I'm wanting you to put the acid and the conjugate base pairs, and I want the strongest over here and the weakest down there. Okay? So, what have we got here? The first thing is NO3 minus. First of all, do you think that's going to act as a base or an acid?
Base.
A base. Can it donate a proton? No, it doesn't have a proton to donate, right? So, therefore, it can't donate a proton, it can't be an acid, but it could accept a proton, so it can be a base. And if it accepted a proton, what would it look like? Pardon? HNO3? Is that what you're saying? I honestly just can't hear you. HNO3, have you seen that before? Do you know what it's called? Nitric acid? Oh, yeah. Okay, so nitric acid and the nitrate ion are conjugate acid-base pairs. Okay? What about NH4 plus? Base or acid? Oh, pardon me, I'll do this. Acid? Acid? Okay, so it can donate a proton? Okay, and what would it become if it donated a proton? NH3 minus?
NH3.
NH3 neutral. It loses H plus, so it becomes NH3 neutral. Okay, so far I've got HNO3 and NO3 minus. I've got NH4 plus and NH3 neutral. And what about this? HCOO minus. Can it accept a proton?
Yes.
So it is called a
Base.
and if it accepted its proton, what would it look like? HCOOH, also called methanoic acid. Everybody see the COOH there? Methanoic acid. Okay? So this could become this. Can this donate a proton? Oh yeah, it can. Here's a proton it could donate. And if it donated that proton, what could it become? It's not going to donate it easily. Let me just be really clear about that. HCOOH. No, sorry. I mean C. Oh, sorry. I was going the other way. I could make COO2 minus. Is what I meant. And then it's an acid, and this is the conjugate base. Does that make sense? So that makes this, what do we call this? Amphiprotic. Protic being proton, amphi being like an amphibian, both things. Okay? Okay, so amphiprotic, meaning I can gain or lose a proton. Okay, now list them in order of strongest to weakest. Can you find your strongest acid on that muddled mess there? Do you think nitric acid, ammonium, I should probably have done these in a different color. Do you think nitric acid, ammonium, methanoic acid, or that ion is going to be your stronger acid? Strongest acid? Nitric acid? Yes? Yes. And what's the conjugate base pair that goes with it? NO3 minus. The next strongest acid, what do you think?
How do you know that's the strongest acid?
How do you know that's the strongest acid? How do you know? Left from where? No, you knew. You looked at your data booklet? Tell me? No. How did you know? Because at some point in your career, in your student life, some good teacher said to you, these are strong acids. nitric acid, hydrochloric acid, sulfuric acid, and you went, okay, at that point. And it kind of stuck. You didn't really know how it related in a table to strong and weak acids, but in your head, you knew that that belonged as an important acid. Important being strong. Okay? That's how you know. Because it stuck at some point. Okay, so methanoic acid. What do you now know about, from the organic unit, about carboxylic acids?
Weak acid.
They are weak acids. In fact, you might have gleaned a bit of that information somewhere along the way of junior high when you looked at vinegar on the pH scale and did that little, rainbow poster that everybody does, right? Where you label and you put a vinegar as a weak acid, right? Or maybe you gleaned that in Science 20 when you were talking about acids, maybe. Anyway, but definitely in the organic unit, carboxylic acids are weak acids. So you know that that's going to be, do you think though, in your gut instinct, do you think it's going to be a stronger acid than ammonia ion or a weaker? What's your gut instinct say?
Weaker.
Ethanoic acid compared to ammonium.
Weaker.
Think it's going to be weaker? You think methanoic acid is going to be weaker? Hands up. I mean, really, I don't expect you to know this answer, so don't worry. Hands up if you think methanoic acid should be a stronger acid. And hands up if you think ammonia should be a stronger acid. Okay, this is how you find out. Look in your data booklet, page 8 and 9. And we're going to get there until later on, but we'll get there now. You guys don't have a data booklet between the two of you? And find methanoic acid and find ammonia. Ammonium. Methanoic acid is higher. Okay? Everybody see those two? Everybody see how you confirm? But hey, guess what? If it's called methanoic acid, it's probably a stronger acid than an ion, ammonia. So that, your gut instinct. But for that, that's just a, how much have you gleaned of the extra stuff in your chemistry career. But, really, even I might want to just sneaky peek a look for those middle ones. So don't feel that I'm not, criticizing you for not knowing. But definitely that one, then those two. And then, what was the base pair of this one? COO, HCO minus, pardon me. And the base pair of that one is NH3 gas, right? We're missing one. We're missing this one. Is this in your data booklet as well? It's not? You don't have HCO minus on the left-hand side anywhere?
Yeah, we have HCl.
No, CO minus. It'd be nice if it was, because it'd make a really good lesson all of a sudden. Okay, if it was in your data booklet, it'd be down here. I mean, like really far down, because it would be an incredibly weak acid. In fact, I'm not even sure if I can think of a reaction that would actually make this lose its proton. Okay, so, but technically, theoretically, it can act like an acid. And you would end up forming its conjugate base of COO minus. And the reason I wanted to make this point,
Isn't it 2 minus?
oh, thank you, 2 minus. What color was that? Red, and actually I need to make it blue. Okay, and I want to make the point that in your data booklet, you can find the amphiprotic ones on both sides. So when we're looking, do you remember how we sort of looked at, for our unit 2, when we were looking at voltages and stuff, sometimes you could find Fe2+ on one side and the other side, and you just had to pay attention to those ones. Similarly, you just have to pay attention that you're going to find the amphiprotic ones in two different spots. So don't get thrown off. Oh, there it is, I'm done. Oh, no, wait. Okay? So same thing as the Fe2 plus in that other data booklet. And same thing as the voltage. The higher up on this side of your data booklet, the stronger the acid. And guess what? Down here, what do you think about these? The stronger the base down here. So these are strong bases, and these are strong acids up there in your data booklet and on this table. Get it? Okay, so conjugate acid-base pairs, tick. Strongest acid to weakest acid, tick. The opposite end of the scale is the opposite strong base to weak base, tick. We're good? Good. So another amphiprotic substances. Can we think of some examples now? Water. Can we think of another example? HCOO minus. Can we think of another example? Pardon?
H3.
So another carboxylic acid?
Yeah.
Okay, let's not pick another carboxylic acid. Let's pick something. Because you're not going to see very many carboxylic acids. HSO4 minus. What is that familiar? Because that's not going to be familiar with. So I'm going to write this in a different color so you can see it. HSO4 minus. What does that look like that is familiar for you? H2SO4. Okay, I'm running out of word space here. Okay, H2SO4. What happens when H2SO4 donates a proton? It becomes HSO4. And when that donates a proton, it becomes SO4 2 minus. Do you see that? How we can go through two stages here to give up both protons. So here it's an acid, conjugate base. Then here it's an acid, conjugate base. Okay? This is becoming an incredibly messy board. I apologize. So do you know what? I'm going to write it. I'm going to just do this, do this, do this, do this. Okay, so amphiprotic substances. H2SO4 would be an acid, always, can't be base. It would become HSO4 minus. That would be its conjugate base. But this can act as an acid too. HSO4 minus could donate another proton and become SO4 2 minus. Again, being an acid and a conjugate base. HSO4 2 minus is amphiprotic. H2SO4, here's another new word for you, is called polyacidic? Polyprotic? Must be polyprotic. Ah, the names just slipped my head. I'll look up. The other one, polybasic. So this one seems to be like it should be polyacidic, but that doesn't sound right. Polyprotic sounds good to me. I think it's polyprotic.
So it's HSO4 minus.
Hold on. It is polyprotic. Polyprotic. Because I can give up many protons. Sorry, Abby? Okay. Okay. Amphiprotic, like an amphibian. Both sides of the fence. Can do both things. Can be acid or base. Right? Polyprotic, many protons. This has many protons, too. Can you think of another polyprotic substance? H2S? Tell me when H3PO4. Is that familiar with you guys? Hands up if you've seen H3PO4 before. Okay, what's it going to become when it gives up one proton? H2PO4 minus, is H2PO4 minus amphiprotic? Yes, because it could as well give up another proton and become HPO4 2 minus. Is that amphiprotic? Yes. So HPO4 2 minus could give up another proton and become PO4 3 minus. Okay? And you can do that with all polyprotic substances. Okay, moving on. I think I've sort of overextended my 20 minutes on this, but anyway, it's all good stuff. Another concept from Chem 20 that I hope you remember, but you might not. So this is a picture diagram of a strong acid. This is a picture diagram of a weak acid. I really like to use this because it shows you in a little bit more picture diagrams. So this is, for example, a strong acid like HCl. So here's your Cl minuses, Cl minuses, Cl minuses, Cl minuses. Here's your H pluses. Okay, and we've got H, what was that, green, Cl. And the HCl will 100% ionize. So we say fully ionize into H plus and Cl minus. Aqueous, aqueous, aqueous. Fine, that's Chem 20, fingers crossed. Chem 30 is maybe in Chem 20, if your teacher kind of pushed you to the limit, would have forced you to write a full arrow here and only partial arrows here, maybe, but certainly in Chem 30 I'm expecting that of you now. And also the addition to Chem 30 is this. We wouldn't just write HCl by itself anymore. We would say plus H2O, and that's going to make not H plus anymore, but rather H3O plus, because that proton needs to piggyback onto the water, and Cl minus. Again, still all, well, not all aqueous. Aqueous, aqueous, liquid, aqueous. Okay? Everybody all right with that? Then the weak acid, try to find the H pluses here. Here, oh, there's one. Nope, that's it. Then we've got H, H, and H, and H. And your X's, there, 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 and there. What's different about these pictures? There's only one that has ionized, and the rest have stayed together. So we say that they partially ionize. How do you spell partially? Thank you. Okay, they only partially ionize. For example, as we were talking about in the organic unit, like only 1% become H plus and Cl minus, and 99% might stay together, hence the diagram. And so an example of a weak acid would be, ethanoic acid. So here's your H. Here's your CH3COO. And this becomes, oh, and plus water, right? In Chem 30 now. And so that becomes H2O. You boys don't need to write any of this down here? None of it? I think you should write it down. And this becomes what? H3O plus and CH3COO minus. Aqueous, aqueous, liquid, liquid often. Sometimes aqueous. Yes, your short-term memory might be great. So you might know these partially ionized fully ionized, but I can guarantee these are marks you drop on your quizzes and tests because you don't write them down. Okay, Evan.
Just as a question for strong acids, would you write like 100% ionized or 99%?
Nope. By all intents and purposes, fully ionized. Fully, all of it. Okay? Whereas the other one exists in equilibrium, and we could draw a K constant, and we could draw a K expression, and we could do an ice table, and we could, etc. Okay? All right, and we are going to be concentrating mostly on weak acids in this unit. Strong acids are kind of old news. They're Chem 20. Okay? Fully ionized, 1 mole per liter of this is 1 mole per liter of this and 1 mole per liter of that. Done. You did that in Chem 20, right? Whereas this, 1 mole per liter of this, from your ice table, doesn't mean 1 mole and 1 mole, does it? You got to figure out what the K value, what the concentration are at equilibrium, and et cetera, et cetera. So this, hard stuff, Chem 30. This, easy stuff, Chem 20. Okay? All right. So then, I think we're done. Hands up if you get conjugate acid-base pairs. Okay, so let's move on then. So, I'm just going to